All right, let's take a look.
So what we were looking at yesterday, remember, let's kind of put this in a little context. So we did a couple things, right? We added up an area under a curve, and we looked at the example of f of x equals x squared first. We looked at a specific example. We want to add it, we want to estimate the area under the curve f of x equals x squared from x equals 1 up to x equals 4, right? And we did that two ways. We picked, just kind of randomly picked a set of inscribed rectangles with width 1/2, and then we calculated the set of circumscribed rectangles of width 1/2. The inscribed rectangles in this case, well, they're always going to undershoot the value, right? And the circumscribed set is going to overshoot the value, and halfway in between is a pretty good estimate, right? It's going to be a little bit off, right? Because this had an upward concavity, the inscribed rectangles are going to be a little better prediction than the circumscribed ones, right? But very slightly, okay? But more importantly, what we talked about were some strategies for getting better estimates, right? What did we say we could do in this case to get a better estimate than the sum of the blue rectangles and the orange rectangles that we currently use? Okay, so we're gonna let the number of rectangles get bigger, right? As the number of rectangles gets bigger, they're going to more closely approximate the curve, right? You'll get kind of a saw edge, but the saw edge, they're going to be really, really small differences between the actual curve and the estimated curve. Yeah.
Is this also known as the coastline theory?
As what?
The coastline theory?
No, but it relates to the coastline theory. Yeah. Yeah, this is, coastline theory just says that, well, you tell me, what's coastline theory?
So if you measure a coastline in, let's say, 100-yard increments, it'll be a certain distance, but then if you break that down to 50-yard increments, they get more accurate, and you're able to fit more increments in the same coastline. So the smaller the increment of measurement, the more coastline there is, and you can actually get like an infinite, you can get an infinite perimeter surrounding a fixed area.
Right, you can. And probably a better vehicle for exploring that would be something like the Mandelbrot set, where if you look at fractals, there's no limit to the complexity of a fractal. And we'll look at this stuff at some point in here. We just need a data kind of between big topics, and we can look at some. We can look at the Mandelbrot set a little bit. If you focus in, it's a fractal, and so that means that the level of detail is the same on any scale, right? So if you zoom in, you still see the same level of detail. And so there is no limit. I mean, if you're going to walk the perimeter of some enclosed fractal, some set, like the Mandelbrot set, you're going to walk infinitely far, because no matter, there's an ever increasing, you can't ever get around a point, because between here and there, there's an infinite number of details, right? If you focus in further and further. So yeah, you end up with an infinite perimeter around a finite shape, which is possible to do. It seems weird, but it's entirely possible to do. Okay? This is indirectly related to that, right? But the idea here is that the area under the curve is finite, right? But by letting the number of rectangles go to infinity, as long as we're going to make the stipulation that each rectangle is the same width, what's that going to do to the width of the rectangles? They're going to get tiny, and they're going to approach 0, right? And so you end up with an infinitely accurate estimation, which is the value of the area under the curve, right? So our goal then is we want to try to take this process that we sort of explored with this specific example, and as always, we want to generalize this. So we're not relegated to just f of x equals x squared, right? It could be any function. And we're not relegated to going from 1 to 4. It could go over any interval, right? And, so that's our goal. So we started looking at this more generally. We took just a random generic function. We used, this happens to be x squared, but it wouldn't have to be, right? It's just f of x. And we started to explore how we could do this completely generally, where instead of letting the lower boundary of our area be 1, we're just going to call it A. The upper boundary, instead of being 4, is now B, right? The function is now just plain old f of x, and the number of subintervals, instead of being 6, like it was in our specific example, is just going to be n, right? So if that's the case, we made some progress here. We said, okay, if we're going to divide this thing up into n equally wide subdivisions, then all we would have to do is define the area of a generic rectangle, right? And then add up each of those contributions. And the vehicle for doing that is a discrete sum. And that's what we kind of left off exploring, was this concept of a discrete sum, right? So if we want to add up, you know, if I've got this sum of I from 1 to 10, well then that means I'm just going to add up each term I as I steps sequentially from 1 to 10. We kind of closed off with this example I gave you guys here of something like, what if I gave you 1 plus 1 plus 4 plus 1 plus 9 plus 1? If you can link each one of these terms to an index variable, then we can add these things up. Well, if we rewrite this in the form 1 squared, should make that 1 squared, plus 1 plus 2 squared plus 1 plus 3 squared plus 1, etc., etc. Well, then we can pretty clearly see that this is just a sum of I squared plus 1, right? As I goes from 1 to however far we want to go, however many terms we're adding up. I think we said we were going to add up 10 terms, right? So then we could write this as, so we're going to do 10 of these things. Then this is just the sum of I squared plus 1 as I goes from 1 to 10, right? Okay, and there are some, so what can we do with this? I almost think we need to just spend maybe, before we try to jump into more of the process of adding up areas, let's just talk about discrete math for a little bit, because you guys didn't cover that last year. And you need to have an idea how discrete math works, how you can add up sums and, sums and sequences, discrete sums and sequences. Because really where we're going to go with this in calculus is calculus just takes macro sums like this, discrete sums, where I is going to move from 1 sequentially to 10 as you move through the whole numbers in between. And we're just going to infinitify that, I guess is how in calculus. We're going to add up sums where instead of adding up discrete steps, we're going to let the steps go to 0. We're going to let them get vanishingly small. And so we take a macroscopic discrete sum and we turn it into a smooth continuous sum. That may not mean a lot right now, but in the back of your mind, I want you to kind of store that thought, because you'll see that that's what we do. That's what the second half of calculus is. Integral calculus, we end up learning that the process of integration is really just adding up vanishingly small pieces, but an infinite number of them, okay? So, what do we do with this stuff? Where do we start? We just got to talk about discrete math a little bit. So, what are some properties of discrete math? If I'm doing a sum of I squared plus 1, just use your intuition here, and you're going to be right. Can you think of a way that I could maybe rewrite this more efficiently? Like up here in this sum, I grouped these by term, but I could regroup that set, couldn't I? Those parentheses aren't really accomplishing anything other than just organizing things for us. Nothing's being distributed over each of those groups, agreed? So I could just as easily, if I take that, let me just grab this sum. And let's explore this a little bit, right? I don't really need those parentheses. So I could write this as 1 squared plus 1 plus 2 squared plus 1 plus 3 squared plus 1, etc. Right? How might I regroup those? Okay, sure. So I could, how about if I take the squared terms and let's group those together, right? So I've got something like 1 squared plus 2 squared plus 3 squared plus, etc., all the way out for as many terms as we want. And I tell you what, instead of saying 10 terms, why don't we just say n terms, and we can let n be anything we want to. Right? So then at the end of that, right, at the end of that, we're going to do plus n squared, right?
And then
So you get what I'm saying? So we're going to add these up through n. And now if we let n equal 10, well, then we've just added up 10 terms, right? But just generically, we could write it that way. Plus
n.
1 plus 1 plus 1 plus n times. Exactly. That's what it's going to be, isn't it? We've got n terms here, and they're all just ones, aren't they? Right? Okay, so then, yeah, so you're getting the hang of this, right? So then what would this look like as a sum? Well, this just looks like the sum of what? Well, okay, but not x probably. I, because I is our index variable, right? So I counts which term we're on, right? So this is just the sum of I squared as I goes from 1 up to what? N, sure. Okay, right? Plus, what's this? That's the sum of 1, right? We're just adding up, each term is just a 1 as I goes from 1 to
1 to
n. Okay. Well, you already told me what this answer was, right? Right, John, what would you get for an answer for this? N times 1, which is n, right? So we know that the sum of some constant from 1 to n is just that constant times n. So we could generalize that a little bit and say the sum of k as I goes from 1 to n is just kn, right? So that's a property of sums. Okay? That's you've got an idea of, why that is. You're just adding up this number n times, which is the definition of a product. Right? That's just kn. Okay, what about this one? Well, this one's a little trickier, right? If we wanted to try to come up with a formula for this, and in the past I've actually done this. It's kind of fun. You use a little bit of inductive math. I'm not going to do that today, though. I think this is something we'll save and come back to later, because it's kind of a separate topic. Right, the goal here is to come up with a formula for this. Man, it really is pretty fun though.
Not too much fun in one day.
Yeah, we better, let's take a look. Why not? Why not? Here's why. I mean, I just think you guys need to have a little exposure, because you didn't really do a lot of inductive math last year either then, right? Like defining, if you have an inductive process, you define the term n in terms of n minus 1th term. Did you ever do that stuff? Okay. Yeah, I think you need to see some of that stuff.
I think we might have done a little bit of that.
What's that?
I think we did a little bit.
A little bit of that? Okay, well, let's get a refresher on that. So what is this one going to be? The question now is, what is that, right? And we can put it in our calculator, right? But right now, that's our only option, because what if n is 1,000? You're not going to sit there and add up 1,000 terms. I hope not, right? That's too much to do. We got to come up with some kind of a formula that's going to make a prediction about what this sum is going to be in terms of the number of items in the sequence, right? The number of terms in the sequence. So in terms of n, we should be able to predict what the outcome of that is going to be. So let's try this. Let's start with an easy one. What is the sum of I going to be? Oh, gosh, one last thing. Sorry, I'm jumping around a little bit, but one thing I want to draw to kind of some closure here. So if we're adding up then the sum of I squared plus 1 from 1 to 10, what was the first moral of our story? What were we able to do with this? We broke this up into separate sums, didn't we? Right? The sum of I squared plus the sum of 1, right? That's important. It's not a real profound thing, but I want to make sure we get that piece out of what we just did. So we could write this as separate. In other words, we could sum this term by term, right? We could break this, if I'm taking a sum of multiple terms, I can take the sum of each term separately, right? So this is the sum of I squared from 1 to 10 in this case, plus the sum of 1 from 1 to 10. I can deal with them individually, right? Now the question is, this one we already know how to do. That's pretty easy. But now what about the sum of I squared? How do we get an answer to that? So let's focus on, how about just the first 3 powers of I? So what's the sum of I? Yeah. Say it again. Go back. Yeah. To that one or the blue one? So that's right there. Yeah. Okay. So, you good? Okay, so what about this? What's the sum of I from 1 to n? Okay, let's just, how about if we make a little table and see if we can come up with a formula based on the table. Okay, this is an inductive process. So this is just going to equal 1 plus what? 2 plus
3, 4, 5.
Right? Get the idea? Okay, so if we make a table then that represents this, we've got, how about if we've got the sum? Okay, so we've got, I'm going to call this S of n.
Is this a new problem?
Yeah, so now what we're trying to do is we're trying to come up with, the goal here now is, how could we predict what that is, right? The sum of 1 from 1 to 10 is just 10. We know that one was easy, right? We came up with a formula for this. The sum of some constant from 1 to n is just k times n, right? But the other parts are a little harder, right? We want to be able to make a prediction here. When we get the problem down to here, we can solve this part, but we don't have a formula for adding up this sum, the sum of I squared from 1 to 10. Our only option right now would be, our only reasonable option would be to rely on our graphing calculator, right, to tell us what that sum is.
So should I have I squared on my one?
Well, okay, yeah, we will. We're going to do the sum of I and the sum of I squared and the sum of I cubed, and that's it. We're not going to go any further. But we're going to see if we can come up with formulas for those. So this is kind of a pre-calculus issue that we've got to resolve before we can go further with our calculus, right? So let's deal with this one, right? So we're going to make a table here. We're going to call this sum S of n. It's going to be a function, really, isn't it? Because depending on what n is, we're going to get different results, right? If n is 3, we're just going to get 1 plus 2 plus 3 is 6, right? If n is 4, we're going to get 1 plus 2 plus 3 plus 4 is 10, right? Okay, so let's make a table then. I think that's this way. So we'll go n and S of n. So if n is 1, what's the sum? 1. If n is 2, what's the sum?
3.
If n is 3, what's the sum?
6.
Okay, and this is getting pretty easy to do. What's the pattern? If n is 4,
It's 10.
it's 10. How are we getting this?
Add n to S.
Okay, good. We're adding the previous sum. We're adding the next term to the previous sum, right? Okay, no big deal. So 10. 5 is
15.
15. 6 is
21.
etc., right? And so our goal, if we could just answer, this is really what we're looking for, this is the Holy Grail, is if this is n, what goes there? Once I know that, that's the goal, right? That's all we're trying to find. If for the nth term, what is the cumulative sum up through the nth term, right? So, how are we going to do this? Suggestions? I mean, that's kind of right. If we can find this I mean, you're sort of thinking about this in the right way. Can we see some patterns here, though? I want you just to stare at this, talk amongst yourselves for a second, see if we can't come up with something interesting. And I'll give you a hint. You could, if you wanted to, add extra columns here, if you want to.
Oh, I remember doing this.
You do remember doing this?
Yeah, I remember doing something like this.
Okay.
I won't do anything yet.
Give you a little hint here. What if we added the column n plus 1? So when n is 1, what's n plus 1? Okay. Do you notice something?
S
What do you think?
plus N plus 1.
N plus S.
Okay, but now our goal is, we want to kind of mix these up. Our goal is we want to be able to come up with a way of predicting the values in this column from the other stuff. Right? So how can I use the same algorithm to get 1 from those two numbers,
Is it
and 3 from those two numbers, and 6 from those
Is
two
it-
numbers?
N times N plus 1 divided by 2?
That works, doesn't it? Everybody see that? Right? If I take the product of these two numbers divided by 2, I always get that number. Everybody see that? 1 times 2 divided by 2 is 1. 2 times 3 divided by 2 is 3. 3 times 4 divided by 2 is 6. 4 times 5 divided by 2 is 10, etc. Right? Okay, so then we can make a prediction. If this is n plus 1, what's our sum? What is it again?
N squared plus.
N plus 1.
So, okay, good. So it's going to be n times n plus 1 divided by 2. Right.
You could simplify that to N squared plus.
Well, you could. We just leave it like this for reasons that you'll see soon. Okay, so we just leave it like that. So that's our formula, right? So we can go back up here then, and we can say this is equal to n times n plus 1 over 2. That's
I remember.
generally true, okay? So now what about I squared? Let's try that one. All right, so now we've got the sum of I squared equals what? So that's just going to be 1 squared plus 2 squared plus 3 squared all the way up to n squared, right? So let's make another column here, or let's make another table where I'm going to have n. We'll call this S of n again. I've got n, leave some space here. So we're probably also gonna wanna have, while we're at it, let's maybe do n squared, right? Just so we can, it's easier to keep track of this stuff. So if n is 1, 2, 3, 4, 5, what's n squared? 1. Okay, so we ought to be able to add these up then, right? So the first one is just gonna be 1. Second one is gonna be what? 5, gonna be 1 plus n squared, right? What's the next one gonna be? 5, well, 5 plus 9 is 14. And 14, our current sum plus the next one is 30. 30 plus 25, 55, all the way down to, that's what we're looking for, right? What is the sum of through n terms of that expression, right? We're gonna have I squared, okay? So this one might be a little tougher. So let's try our old trick. How about, what if we add another column in here for n plus 1? It's a little tougher, huh? This one's a little tougher. How are we gonna get these numbers out of those two? And you're not. You're gonna need another column. It's pretty rare that anybody ever guessed this. It's pretty hard to see this one. What's gonna go
Leave
here?
it for a second.
What's that?
Leave it for a second. You should hold us in class until we.
I think I almost have it. Oh,
I think you got it? What do you got?
it's
N times n plus 1 minus
N times n plus 1 minus n. No.
It-
Okay, what might be useful though is, so I'll do one more thing here.
wait, Mr. Wait.
Yeah.
Is it n plus the quantity n plus 2 squared?
No.
It isn't. Sure?
No, are you sure it's
Wait, no.
No, it's
No,
not.
plus 1.
No.
No?
It's close though. So this could be helpful. What if we just multiply these? I'm going to multiply these by some discrete amounts. Okay. So I'm going to do like 2 times this column. Okay, and that's going to give us 2, 10, 28, 60, 110. And then I'm going to do, how about if I just jump right up and do 6 times. That's so good. Now we could have done all the ones in between, but this one's going to be an important one, right? We could have done them all up through 10 or something. But this one's going to give us 6, 30, 75, so 81, 180.
81
How'd you
can
get
be
it?
divided by 2.
What did I do wrong there? Oh, that's not right. That's going to be, whoops, that's going to be, well, there we go. So it's going to be 84, yeah. So can we make that connection? What other column do we need? That's my big hint is, we need one other column here to get to this column.
So n plus n plus 1 times.
So what do you need to multiply by to get this
7 times 4.
here? What do you got to multiply by? 1 times 2 times what is 6? 3. Here, 2 times 3 times what is 30? 3 times 4 times what is 84? Okay, you seen a pattern?
2n plus 1.
4 times 5 times what is 180?
2n. It's 2n. That column is 2n plus 1.
Ah, okay, right. So how do you get this column right here? How do you get these numbers based on n? Well, this is just 2 times n plus 1, right? See how we got that? So 2n plus 1 gives us those values, doesn't it? Right? See what I'm saying? Okay, so if n times n plus 1 times 2n plus 1 equals 6 times the actual sum, what's my formula, right? Well, we can do a little algebra with that, right? So we've got n, whoops. So we've got n times n plus 1 times 2n plus 1 equals 6 times s of n. We're trying to solve for s of n. What do I do?
Just divide by 6.
Divide by 6, yeah. Right, so there's my formula then. So to get these numbers right here, it's just these numbers divided by 6, right? So it's going to be n times n plus 1 times 2n plus 1 over 6. Okay, and so we got an answer. There's our formula for adding up the first n terms of I squared. Okay, now I'm just going to give you the one for n cubed. No, it's close, but that's not it. It's the right idea. So to add up the sum of I cubed from 1 to n, you just get n squared times n plus 2 squared over 4. I think that's right. N plus 1 squared over 4 was. That is right in here. Yeah. Okay, so we've got that string of formulas now, right? So that's helpful to us because now we could go back and, for example, we could finish that problem, couldn't we? Right? So what do we get for our answers then? Well, this one was one we just did, right? The sum of I squared from 1 to n was just n times n plus 1 times 2n plus 1 over 6. So what is that sum? It's only dependent on n, right? So good, 10 times 11 times,
21 over 6.
good. Okay, can I end up with a fraction here? No, can't get a fraction, right? Because I'm adding up integers. So this has to cancel, so I'm going to get 7 and 2, 5 and 1. So I get 5 times 11 times 7. So 35 times 11 is 385,
Yep.
right? So this part's going to be 385 plus 10 equals 395, right? So now you guys, let's practice your calculator skills. You tell me, remind me how I can add this up on a calculator. what do I do? Math,
0.
0, good. It gets us to the template for sum. And this from here is pretty easy, right? I'm just going to let what? X go from,
1 to 10.
and what am I adding up?
X squared.
X squared. Oops. No. Oh, well, I mean, we could. I'm just going to add up this one first. Okay, we'll do x squared plus 1. Why not? Do it all at once. X squared plus 1. And we get 395. What do you know? Okay. Right? So we got some, let's summarize what we know. Right? So let's put all our formulas on one page because we're going to use these things. Right? So we get the sum of k from 1 to n is what? Okay. Okay. The sum of I from 1 to n is
N over N.
times n plus 1 over 2. Good. The sum of I squared from 1 to n was
N squared.
no, n times
N plus 1.
n plus 1 times over 6. And then finally, we'll just finish there. Oops. N squared times
N plus 1 squared.
4. So we got them all, right? Okay, so that's pretty useful, right? So now, we got 4 minutes, is that right?
Yep.
Okay, so this is the last thing then. Let's just, in our minds, let's just connect this to where we left off with this process, right? So our goal then was, and this is where we'll pick up tomorrow, but our goal was we wanted to establish some formula for the area of some generic rectangle that would represent any of the rectangles from the first to the nth, right? We call that the ith rectangle. I is not an accident, right? I is our index variable. Why do we pick I? For that reason, right? Because we're adding up, that's what's keeping track of which term it is, right? That's an index variable. It's going to step sequentially from 1 to 2 to 3 because all it's doing is counting the number of the rectangle in this case, right? So we want to come up with the area of the ith subinterval, and then we can just add all those up. Well, we did that, right? Remember what we left off with yesterday is we said really the width is always just going to be delta x, and all that is the width of the interval, b minus a, right? Left edge, right edge of the interval, divided by the number of subintervals, right? So b minus a over n, okay? So that's the width. Well, what's the height going to be? The height is just going to be the value of the function, in this case, at the left edge of each subinterval, because we're taking an inscribed sum of a monotonically increasing function, right? So all we had to do, courtesy of Marin yesterday, was we just had to start at A and take n, or take I steps to get to the ith subinterval, I steps of width delta x, right? So x sub I, you know, the place where we're going to evaluate the function was just going to be our starting place plus I steps of width delta x, right? And so the function, then the area is just f of that x value times the width. That's the height times the width, right? And so we end up with f of a plus I delta x times delta x is the area of the ith subinterval, right? So if I want to add up the whole sum then, that's no big deal, right? I can do that. That's just going to be, this, right? The total area is just the sum of all of the I rectangles from 1 to n, right? Well, we said that's just the sum of f of a plus I delta x times delta x as I goes from 1 to n. That's it, right? That's the area under the curve with n subintervals. And we gotta remember what delta x is. Delta x is b minus a over n, so I could make that substitution, right? So all I've gotta do to get the exact value of the area is take the limit of this. The exact area is just gonna be the limit of this expression of the sum of f of a plus I times delta x, which is b minus a over n. We're gonna take the limit of that as n goes to infinity, right? So that's what we're building towards. When we can do that, we got it, right? We just got a few more pieces in the puzzle. Okay?